let's recap our trig ratios. And of course, it's all to do with our wonderful right-angled triangle, which of course we know the largest side is called the hypotenuse. Once we reference an angle, then the opposite side is creatively called the opposite, and the side next to the angle is called the adjacent. So the three basic trig ratios that we learn: sine, not sin, opposite over hypotenuse; cosine, not cos, which is adjacent over hypotenuse; and tangent, not tan, which is opposite over adjacent. The reason I say that is, and I'm going back a fair few years now, but I still remember the student who, when asked to find the sine of 60 degrees, left the question blank because they didn't know what they were talking about. It was sine. No, it's the sin of 60, isn't it? Not the sine. So remember, they're just abbreviations for the actual words. We also have what we call the reciprocal ratios. So the three basic ones, upside down. I always wonder why on earth they named it this way. To me, it would be more logical to have cosec go with cosine, but for some reason they don't. I suppose just to confuse us, and it works. So the reciprocal of sine is actually cosecant, abbreviated cosec. The reciprocal of cosine is secant, abbreviated sec, and the reciprocal of the tangent ratio is the cotangent ratio. I suppose we don't really use them that much when it comes to actually doing trig questions as far as finding sides and angles, because on our calculator we don't have those buttons. We have the three main ones, so we tend to convert everything into sine, cosine and tangent. So alright, sine x equals cos 25. It is a trig equation. We have to find x. What would x be and why? That brings me to my next point then. Why is the cosine ratio called the cosine ratio? Because it's which, sorry? Say it again. The word? Complement. Thank you. Complement. And you remember from geometry, complementary angles add up to 90 degrees. So therefore, the cosine, or the complement of sine, is 25. So sine would be 90 minus 25. The two angles will add up to give 90. So 90 minus 25 is 65. So if I get an interesting question like this, the cotangent of x minus 20 is equal to the tangent of x plus 30. Well, complementary ratios. So I know the two angles should add up to give 90. So the actual equation they're asking me is x minus 20 plus x plus 30 is 90. Oh, that's easy enough to solve. We get x equals 40. All right, there's pretty much three basic right-angled triangle trig questions we could have. One is where we find the side, and the side is not the hypotenuse. So we set up our trig ratio based on the angle that we know. We have opposite and adjacent, so we'll use the tangent ratio, a over 13, multiplied by 13, punch some numbers on our calculator, making sure the calculator is set to degrees, and we get what's one decimal place, 23.5. The second type is when the side that we're finding is in fact the hypotenuse. So when we set up the ratio, in this case it's the sine ratio, the pronumeral ends up on the bottom of the fraction. I mean, I could use the reciprocal ratio and say x over 5 is the cosecant, yes, cosec of 32, but it's not really going to help me because I don't have a cosec button on my calculator. So I leave it with the sine. So to get the x, I divide by. So rather than putting in the middle steps, I mean the middle steps would be 5 equals x times sine 32, so therefore x is 5 divided by sine 32. Simplest way I remember is simply, well, if the pronumeral is in the top, I'm going to multiply by the number. If the pronumeral is in the bottom, I'm going to divide by the number. Well, when I say the number, I mean the trig. So I multiply by the tan 61, here the x, I divide by the sine of 32, 9.4. The third type, of course, therefore, is finding an angle. So the cosine of theta is 10 on 14. To undo cosine, I have to do its inverse function. And the inverse function of cosine is, it's known as the inverse cosine function. Okay. And it's symbolized with a -1 there. If you look on your calculators, on the cosine button, above the cosine button, you'll see cosine with a -1 on it. And that basically means is I'm finding the inverse cosine function. Some textbooks, instead of using inverse cosine, probably more older textbooks, they call it arc sine. So arc cosine, you might see. This explains why we have reciprocal ratios. Because when you see the -1 there, it's sometimes you think about it and say, oh, it's to the power of -1, which means 1 over. So we never do trig to negative powers. So we can't get confused with the inverse functions. So that -1 means the inverse function. It does not mean cosine to the power of -1. Okay? That's why we have the reciprocal ratios. All right, we can go to our calculator, and what do I get? 44 degrees, 25 minutes. The exact ratios, there are ones that we should just know. How do we get them? Here's a triangle. It's an equilateral triangle. All of the sides are 2. All the angles obviously are 60 degrees because it's equilateral. I can chop that triangle in half. I now have a 30-60 triangle. Sides 1, 2, bit of Pythagoras. The third side is the square root of 3. I can now read off that triangle the exact ratios for 30 and 60. There's 30. Sine of 30 becomes a half. Cosine 30, root 3 on 2. The tan of 30, 1 on root 3. I can also read off the ones for 60 degrees. And we notice something very interesting happening. The sine of 60 is the same as cos of 30. 60 and 30 add up to 90. Sine of 30 is the same as the cosine of 60. Once again, 30 and 60 add up to 90. The complementary ratios are the same. So if you ever forget those ratios, sometimes it's easy just to remember the triangle and then you can draw it up. In fact, those who have a math aid, you'll find that that triangle is actually on there and you could just read it. Now, the 45-degree triangle. It's an isosceles triangle. We have the sides equal to 1. By Pythagoras, the other side then is root 2. And we can read off the ones for 45 degrees. Sine of 45 is 1 on root 2. Cos of 45 is 1 on root 2. They're the same. That's because 45 and 45 equal 90. They're complementary ratios. And tan of 45 is 1. Another way of remembering the exact ratios is this pattern. 0, 30, 45, 60, 90. Sine of those angles goes square root of 9 on 2, square root of 1 on 2, square root of 2 on 2, square root of 3 on 2, square root of 4 on 2. And they give you the exact ratios for sine. Don't know if you've ever seen that pattern before, but it's kind of neat. Whilst we don't always write it that way, I mean, sine of 90 we don't normally write as square root of 4 on 2, but the square root of 4 is 2, 2 on 2 is 1. There's the ratio. Cosine goes the other way down. So it starts at the square root of 4 and goes down. Square root of 3, square root of 2, square root of 1, square root of 0. And then to get tan, remembering that tan can be written as sine divided by cosine, then it's just the numerators divided by the numerator. So I have root 0 on root 4, root 1 on root 3, root 2 on root 2, root 3 on root 1, and root 4 on root 0. Ooh, yuck. Tan of 90 does not exist. Can't have 0 on the bottom of a fraction. So that's another way of remembering those exact ratios. Measuring angles. Okay, angles of elevation. Hey, I'll just wait. You have something to contribute? No? Thought it must be important. You must be reassuring him in the corner there. He's getting very upset about trig. And so you were consoling him because I saw you give him a nice calm pat on the hand, which is very nice of you. All right. Angles of elevation. We elevate from a horizontal. So we say it's in reference to where we are. So if the angle is at A, I'm at A. And I'm elevating, I'm looking up to B. So it's the angle of elevation of B, what I'm looking at, from A, from where I am. Angle of depression is then when we lower our eyes. So of X, I'm looking down at X. From Y, I'm up at Y. The interesting thing is, of course, the angle of elevation is always equal to the angle of depression. If there was someone up there looking down at you, it'll be the same angle because of alternate angles. They would have to be the same. Bearings. Now, they of course are the main compass headings. If we go exactly halfway, we do things like saying northeast. We start with the vertical ones always. We never say west-south, it's always south-west. And we could halve those again. Again, we start with the more important one. So we would start with the blue one, not the red one, if you like. So it's north-northeast, not northeast-north. And it's east-northeast, not northeast-east. You start with the higher up in the level. Theoretically, I could divide that again. And halfway between, let's say, the southeast and east-southeast, halfway between that would be, well, red's the higher up on the level, so I'd start with that one. Southeast, east, southeast. But it starts getting a bit confusing then, so we don't tend to do that. And then we start going to simply, well, I'm going to start at north or I'm going to start at south, and I'm going to go so many degrees towards the east or the west. Now, a true bearing, we always start at north and go clockwise. So there's X, there's Y. The bearing of Y from X, so I'm looking at Y, I'm standing at X. In this particular one, if that's 30 degrees, that would have a true bearing of 120 degrees. Start at north, go around. The compass bearing would be south, 60 degrees east. Start at south, how many degrees do we go to the east? If I'm at Y and looking at X, then that would be 300 degrees as a true bearing, and as a compass bearing, north 60 degrees west. Okay, now look, you'll see I've said in 1 to 3, just pick some. I think if I remember correctly, they're just calculator ones to make sure, oh yes, you know how to use your calculator.